University, who's going to speak on the stable homotopy theory of invertible spin systems.
Thank you for introduction, and I'd like to thank the organizers for inviting me and giving me an opportunity to give a talk in such a wonderful conference. And I think I need to start with introducing myself, because I do not belong to the mathematical physics community. Maybe my past research interest was commutative geometry, K theory, X theory, and so on. And I'm still going in that direction, walking in that direction. But recently, I'm changing my research area from geometry to physics in a branch of mathematical physics, condensed matter physics, namely the topological phases of matter. And recently, I published one preprint and with the same title of this talk, and with the archive numbers as here. And I want to explain in this talk. I want to explain about the topic contents of this paper. It has 100 pages or more, so I think I can't explain everything, but so I want to focus in this talk on the whole story of my research. In this research, I solved the conjecture by Alexei Kitaev, which is proposed by in 2013, and which was one of the guiding principles of this area in this decade. And indeed, my first research interest, namely the cost geometry, it can be used efficiently to solve this problem. And this is what I want to explain in this talk. Okay, let's start. I want to start with explaining my target of this research. What I'm interested in is that this set, the set of smooth equivalence classes of smooth maps from some given manifolds M. Namely, for example, it can be sphere or torus and so on, from some given manifold M to the set which is denoted by IPD. The IPD is a space of all possible d-dimensional Hamiltonians. Here, this is indeed a misleading notation in the sense that this is a little different from my the notation of my paper, but I want to use this misleading notation in this talk. This is a space of every Hamiltonians of dimension d. Here, for the word Hamiltonian, we assume the following three assumptions: short range, gapped, and invertible. We assume that Hamiltonian is short range first. This short range means that we are all nearest neighborhood interaction, and second nearest, third nearest, and blah, 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 and so on. And we need not restrict ourselves to finite range interaction. We are all infinite range interactions, but we assume that the long range terms decays rapidly, very rapidly. This, and the second assumption is the spectral gap. We assume that Hamiltonian has a unique ground state, at least locally, and has a spectral gap above it. And the third assumption is invertibility. This is a kind of topological assumption. We assume that H has an another Hamiltonian, which is should be called the homotopy inverse of H, namely the product of H and its inverse, namely H check, is not the trivial, but it's homotopic to the trivial Hamiltonian. This is the meaning of the invertibility. Okay, these three assumptions will be made more explicit later.
What is a product?
Sorry, products. It's a how to say composite of two quantum systems. Does it make sense? Okay.
Yeah.
Thank you. Okay.
You're working on a spin system? Is that right?
Yes, right.
Can you fix the local Hilbert space dimension?
No. So it can be arbitrary, but finite. Okay. Before going to more detailed definition, I want to explain the motivation of our work. Since I'm a topologist, I think, I think there's no doubt in studying the homotopy set, because if for a given topology set, to learn about the homotopy set from some other space to the space of our interest is a very fundamental question for a human being. So there is no doubt. But maybe this is a research originated from physics context. So I need to explain why why we are interested in this set from the viewpoint of physics. The reason is that it can be applicable to the study of symmetry-protected topological phases. Let G be a compact Lie group of symmetry acting on each site. Namely, I will explain the more precise definition of spin system, but if for audiences who know the definition of spin systems, this symmetry acts on the matrix algebra placed on each site, and the group acts trivially on the lattice itself. So, in other words, this is a symmetry acting on the internal degree of freedom. The typical example includes U1 charge symmetry and spin symmetry and so on. And for such a kind of symmetries, to study the kernel of the pi0 group of the G fixed point subset of the set of whole Hamiltonians, namely the set of G invariant Hamiltonians, and to consider the connective component of this set, and consider the map forgetting Z symmetry, namely the map induced from the inclusion of from the G invariant Hamiltonians to the set of non-G invariant Hamiltonians, and consider kernel of this set. In some cases, it turned out by the research of Gu Wen and Pullman, Berg, Tanao, Shikawa, and so on, that this kernel subgroup can be non-trivial in some cases. And indeed, there's no doubt in our interest to the study of pi0 group, because namely the number of connected component, because the connected component of the set of Hamiltonians describe topological phases and topological phase transition. Namely, if you have two Hamiltonians which are both in spectral have a spectral gap and which are both invertible, but if we know that these two Hamiltonian lies in the different connected component of the set of invertible Hamiltonians, then by connecting these two Hamiltonian by a linear combination, then we can show that there is an intermediate point, at least one intermediate point, whose spectral gap is filled. This is a highly non-trivial result because it's very hard, extremely hard to determine the spectrum of GNS Hamiltonian of given quantum spin systems by doing some analysis. But topology this topology can show this kind of spectral gap filling result. So our motivation is concerned with G invariant version of this kind of phenomenon. A typical example of the so-called AKRT Hamiltonian, which have a very explicit form like this, and I don't want to explain the precise definition of this SX, but in it, this has a very explicit form, and this kind of Hamiltonian has a symmetry of the group G generated by 2 Z over 2. This Hamiltonian has a symmetry of this group G, and indeed, we can show that this Hamiltonian is contained in a non-trivial G topological phase. So this is separated from the trivial Hamiltonian. But how can we know the non-triviality of this Hamiltonian? There's a nice topological invariant distinguishing this Hamiltonian with a trivial Hamiltonian, which is called index or G index in the literature, which is given by Gu Wen and Pullman, Berg, Tanao, Shikawa, and Ogata and Kapustin, Sopenka, and many other researchers. Indeed, now we know that for low dimensions, namely D is less than or equal to 2, there is a group homomorphism from the set of these SPT phases to the group cohomology of degree D plus 1 with a coefficient in the torus. which is indeed isomorphic to the d plus 2 degree cohomology of the group with coefficient in Z, because we assume that D is a compact group.
The group structure on the left-hand side, that's this tensor program.
Oh yeah, so this is given by the composite of quantum systems.
Are you assuming this finite group?
No, we can. This can be compactly group in general.
For the last
For the
so the
here?
you can have the rational for non-compact. No, non-finite.
So yeah, indeed it depends on the definition of the group cohomology of compact Lie group, but indeed this is correct for a general compact group. I can explain more detail after the talk, but this is correct for general compact group, not only finite.
That's the group homology.
This is a group. This is a group cohomology. So this is not a cohomology. Cohomology of the topological space G.
No. I thought even for the classifying space.
Yeah. So indeed, this is not the same thing as the cohomology of the classifying space. When D is zero, we can easily get such kind of group cohomology class. Indeed, when D is, so the case D is zero is the usual quantum mechanics. So unique ground state assumption says that the set of D zero-dimensional Hamiltonian is the same thing as a ground state vector, ground state's one-dimensional subspace in the Hilbert space. So this means that set of zero-dimensional Hamiltonians is homotopy equivalent to the set of vectors, namely the complex projective space. And when the G symmetry is taken into account, then the G invariant subspace of this complex projective space is the same thing as a disjoint union of complex projective spaces, where the copy of complete CP infinity is considered for the set of, over the set of characters. So the pi zero of this set corresponds to the set of characters, and each character is correspond to the one cocycles. So this is why zero-dimensional SPT phase correspond to this the first cohomology group. And the case of D equal to 1 is given by Ogata, and in her work on by using von Neumann, the techniques of von Neumann algebra. Indeed, if you have a one-dimensional Hamiltonian, which is invariant under the action G, then its ground state is not to have split property. So with respect to the decomposition of the right and left half of the spin systems, so by restricting the ground state to the right half of the quantum spin system and take the weak closure, then we get a type 1 factor, which is isomorphic to some bounded operator algebra, on which G acts by automorphism. So this corresponds to a projective representation of G, which gives an two cocycle. This story gives an topological invariant taking value in the two cocycle. This is the topological invariant called the Ogata index, and indeed, in the case of a KRT Hamiltonian in the previous slide, this invariant is known to be non-trivial. So this is why we can show that a KRT Hamiltonian is contained in the deep non-trivial phase. This is the case of D equal to 1. And the case D equal to 2 is also probably in the same way, but the situation is more complicated. I think this argument should be called something like projective 2 representation, but I didn't consider about this word seriously. I just feel that this should be something like 2 representation to projective representation, but this is just my fear. And anyway, so this kind of work is done by Ogata and Sopenko almost independently, and okay, in any cases, a group cocycle is obtained by an explicit analysis, explicit and algebraic and analytic argument. But we know that the group cohomology is something like a topological object, and it has a topological nature. So, but moreover, the left-hand side is also something like something should be regarded as an issue of topology. So now we have two set and map from between them, and everything a topology an issue of topology. So I want to understand this morphism in terms of topology more precisely at homotopy theory. This is a very natural question. And another question coming from this observation is that what happened when D is more than 3? Are there any topological invariant taking value in the group cohomology as well or not? This is a very natural question. And to answer these questions, Alexei Kitaev proposed a conjecture like this. And by using this conjecture, we can understand the topological invariant taking value in group cohomology in the following way. Sorry?
So you talk about a two representation on the previous slide. So
Yes.
just I apologize for the stupid question, but this is for a two group or representation of a
I don't think consider seriously. I can't answer. Sorry.
Point is not to do the two group version of G. G is really a group.
Yeah, G is really a group. Right. Yeah.
Representation is some higher categorical version of the higher representation.
Yeah, which should correspond to the 3 cocycle. Something should correspond to the 3 cocycle. Okay. This is a strategy for constructing group cohomology value topological invariant in terms of topology. First of all, we start with a set of invariant pi zero group of the G invariant Hamiltonians. This is this set. And we go to the set of G invariant homotopy sets from the universal free G space EG to the set of Hamiltonians IPD, and then go to the set of non-equivalent homotopy set from BG to IPD, and then go to the homotopy set from BG to the Eilenberg-Maclaurin space. This is the story. There are 3 steps. The first step is very clear. This is given by Purlbach via the projection, so collapsing map from the EG to the point, which is indeed a G equivalent map. So by taking a Purlbach, we get a map from this homotopy set to that homotopy set. But in general, so okay, we know that there is a homomorphism here, but in general, it is not it is not easy to expect that this is indeed an isomorphism. But anyway, there is a map here. And the second map is not does not exist always in the generality of stable homotopy theory. Indeed, the left-hand side is a priori isomorphic to the pi zero set of the the set of sections of bundles with the base space BG and the fiber is IPD.
Sorry, but is IPD what kind of topology you have? Like variety or?
Please look at the here. I wrote this is a space.
Okay, sorry.
Indeed, this is not a topological space. This is
Not. Oh,
this is indeed a diffeological space. So I don't consider it topology at all.
oh. When you speak about homotopy,
Yes. So yeah. So this is the diffeology is a framework for describing the homotopy. So diffeology is a minimal framework for describing smooth homotopy.
okay.
Of here, okay. So the number 2 is a comparison of this set and that set, and they are not a priori isomorphic. And the left-hand side is a priori isomorphic to the set, slightly different set. This is very similar to the right-hand side, but somehow twisted. And if this bundle is a trivial bundle, then this right-hand side is isomorphic to, this set is isomorphic to that set. So we can show that number 2 is indeed an isomorphism, but it's in general not true. And then number 3 is should be induced from some continuous map from IPD to some Arenberg-Maclaurin space if there is some such a kind of map. And what is proposed by Kitaev and proved by myself is that the family of spaces form an omega spectrum. So the precise meaning of the word omega spectrum being omega spectrum is that there is a homotopy equivalence of the set space IPD and the base loop space of the IPD plus 1, the set of D plus 1-dimensional Hamiltonians. This is a precise definition of the word omega spectrum, and here this word spectrum is used in algebraic topology, but it's nothing to do with the spectrum of linear operators. And this is a definition, and what's good, or if we can show that this is an omega spectrum, is that this theorem should concludes that the assignment from X, to M from M to the homotopy set, this functor is indeed a cohomology functor. This is a consequence of this theorem. And this kind of algebraic nice structure enables us to compute this homotopy set efficiently, and indeed this theorem solves numbers 2 and number 3 in our setting. Here, indeed, if, for example, number 2 is solved in the following way, indeed, we can show that more strongly IPD is split G spectrum, not only a spectrum, but also it's a G spectrum and it's a G split G spectrum. This is some property of omega spectrum which is equipped with G action. I don't want to explain the detail, but anyway, we can show something something stronger, and which concludes that number 2 is indeed an isomorphism. This is a kind of abstract nonsense in algebraic topology. And so number 2 is indeed solved by our theorem. And then number 3 is the map from IPD to KZ D plus 2 is constructed in some cases, indeed. So by a consequence of this theorem, we get a map from the Arenberg-Maclaurin space to IPD, which is a connective cover, Postonic cover in topology. But unfortunately, the direction is opposite. So it doesn't seem to be useful for our aim. But luckily, if D is sufficiently small, indeed D is not more than 2, then this map in these splits, namely there is a homotopy inverse, homotopy retract from here to there. So which is the map from here to there as desired. So by a topological argument, by just checking the homotopy groups, we can obtain map from here to there by a very abstract way without any concrete construction. So algebraic topology helps us to define a map from here to there, and eventually we get a map from the left-hand side to the right-hand side without any concrete argument. This is our motivation for studying the set of homotopy sets like this. So if we
every cohomology class is attained by a model.
Yes, possible. At least when G is finite. When G is a compact Lie group, I don't know. Maybe in this one, it's yes. The answer is yes. In this one, every cohomology class can be realized in terms by some Hamiltonian. This is given by very explicit argument, very explicit construction of by using matrix product states and without any abstract algebraic topology. But I don't know much about dimension 2. So this is an this should be a future work by myself or others. It is an interesting problem. Thank you.
You said that there is a map from the Eilenberg-MacLane space to IPD, and there is an inverse of it, right?
So now we can go from here to back to here, but we do not know we can't compare this number 1 map here. This is a non-trivial map. The existence is very easy, but it's difficult to know whether it is a surjective or injective. This is a problem. Thank you. Okay, let's go back to the story. And now we are interested in solving this problem. To construct a homotopy equivalence of the set of d-dimensional Hamiltonians and the loop space of the d plus 1-dimensional Hamiltonians. This is our problem. And indeed, the original motivation of Kitaev may come from the his previous result, which is independently given by Schneider, Liu, Furusaki, Ludwig in the same year, and which claims that the free fermion, which is a simpler toy model of quantum spin systems, is classified by real or complex case theory. The work by physicists, these two physicist groups, is given in terms of physics argument, but this statement itself has an rigorous state formulation in terms of functional analysis of one particular Hamiltonians. And in this rigorous functional analytic setting, this statement is proved by myself in maybe around 8 years ago. And here, I have never explained the definition of the quantum spin system yet, but indeed, for the free fermion theory Hamiltonian is defined in a similar way as the quantum spin system, but we replace every tensor product appearing in the definition of the quantum spin system with a direct sum. So this means that free fermion corresponds to one particular Hamiltonian acting on the Hilbert space of wave function on the lattice. So the analysis becomes extremely easier than that of quantum spin systems. And indeed, the set of gapped Hamiltonians in free fermion theory is the same thing as what has been studied in a different area of mathematics, namely coarse geometry, index theory, case theory, non-commutative geometry. In this area, we are very interested in the set of projections of the C-star algebra, which is called the Low algebra, whose definition is, roughly speaking, similar to the set of C-star algebra closure of the set of Banel operator acting on here, lattice space of the lattice, having the finite propagation, finite range operators. More precisely, there is a subtle difference of the Low algebra and this is algebra. This is algebra is called the uniform Low algebra, and there is a subtle difference between what we dealt with. But anyway, there is a sister algebra defined in this way, right? And so the set of projection of this sister algebra has been studied in coarse geometry with a potential application to the study of differential geometry, for example, so some high dimensional topology or positive scalar curvature and so on. So, but in the first book of John Law, it is pointed out that there should be related to physics, but this is just a slogan. There's no more explanation. Indeed, there's a theorem by Higson-Low-Yu in 1993, which claims that this set of projections is homotopy equivalent to the clustering space of infinite unitary group, which is representative of the complex case theory. So So this means that the set of Hamiltonians of sets of projections in dimension 2D gives is a part of omega spectrum. And indeed, in this paper, it is actually proves that the loop space of D plus one dimensional projection of row algebras is homotopy equivalent to the set of projection of cis algebra of dimension D. So this is exactly the free fermionic version of the Kita proposal. This statement.
By finite range.
It's supported near the diagonal. So you have so in the case of D is 1, we can draw a kernel function of a given operator, and it's an infinite times infinite matrix. And so finite range operator is the operator whose kernel function is supported near the diagonal.
Okay.
And the distance of the diagonal is uniformly bounded by some constant. Thank you. What time did I start? 3? Oh. Okay. So this is a free fermionic version of the Kita proposal, and indeed the short range assumption of appearing here is the same assumption as the short range assumption we assumed in the set of Hamiltonians IPD, and indeed because of the short range assumption of quantum spin systems, the set IPD can be described in terms of coarse geometry. So the proof of Higgson law U works for IPD as well. It works. The same proof works, and indeed, the original idea by physicist groups of Kitaev, Sion, and Guyot Johnson-Fred are quite parallel to the free fermion theory done by Higgson law U, but the underlying analysis is quite different, and we need to be more and more careful in order to follow the same story to in the case of quantum spin systems. This is a precise definition, but maybe I don't have enough time. So I just explain very few about the definition. We are interested in this discrete subset of RD, which we call lattice, and we place matrix algebra on each lattice point and take the tensor product. This is observable algebra, and we are interested in the fresh subalgebra of this C-star completion, which is called the set of subalgebra of almost local elements. Meaning that an element A in the almost local subalgebra is well approximated by some bounded ball in this way. Namely, so this norm is bounded for any function. So measured, so the distance. This means that the distance of an element of the C-star algebra here is with subalgebra supported on some open ball with radius r, decays quickly as r go to infinity, more quickly than this function. The fractional power is exponential of the fractional power. And if we have a family of such an almost local operator such that each hx is supported near x in this way, in this sense, then we can consider the infinite sum of commutators acting on the almost set of almost local elements. And indeed, this is not a finite sum. This is my typo, but this commutator. This infinite sum indeed converges and gives star derivations. And indeed, this is integrated to one parameter family of automorphisms, time evolution on the C-star completion. And indeed, it's a commutator and infinite sum of commutators, and that is integrated time evolution. The Fresher continuous on this subalgebra. And now the notion of ground state, non-degeneracy of the ground state and spectral gap of the ground state is formulated in terms of GNS theory. I want to omit this detail. Now, I want to introduce a precise definition of the invertibility. First of all, we want to we initially fix a choice of trivial Hamiltonian, which we write small h. And our trivial Hamiltonian is chosen to be atomic one, namely, so there is no non-trivial interaction between two different points. And time evolution is infinite tensor product of time evolution on each side. And we define, so I omit the precise definition, but we want to define the composite of two Hamiltonians acting on the tensor product of observable algebra, whose time evolution becomes a tensor product. And so we say that H is invertible if there is another Hamiltonian H check, and there is a homotopy connecting the composite of H and H check and the trivial Hamiltonian initially fixed here. This is the definition of the invertibility. And we are interested in the set of invertible Hamiltonians. And for such a triple, namely H, H check, and H bar, we get a new Hamiltonian of dimension d plus 1. More precisely, a loop of d plus 1 dimensional Hamiltonians in the following way, which we call Kita-F pomp. We start with a trivial Hamiltonian, the infinite trivial Hamiltonian of the trivial Hamiltonian H, like this. And we consider the infinite trivial Hamiltonian of this homotopy, H bar, connecting a trivial Hamiltonian and the product of H and H check. And we consider the infinite copies of composite of infinite copies of this H bar in this way. Then we get a homotopy from the trivial Hamiltonian to the product of H, H check, H, H check, H, H check, H, H check, and so on. And so we can go back to the trivial Hamiltonian in the same way, but the choice of the pairing of H and H check is rearranged in like this picture. So we get a homotopy of one loop of d plus 1 dimensional Hamiltonian. Okay, so this direction is a special direction in the d plus 1 special direction, and there are d more directions in the direction to perpendicular to the screen. So now we get give one parameter family. This gives a map from IPD to the loop of IPD plus 1, and this is a map giving the homotopy equivalence of IPD and omega IPD plus 1. And what we proved is that this is indeed a homotopy equivalence. What is proposed by Kita-F in his talk is that there's a homotopy inverse of this map, which is constructed in some explicit way. And we can follow the original construction by Kita-F, but there are some technical ingredients for realizing the idea of Kita-F. There are 3 ingredients. But the first one is to use the idea of Hastings' diabatic process, which is very standard tool for recent study of topological quantum spin systems. And the second is to use the concept of diffeological space, as I explained, instead of topological spaces, because we are interested in smooth map, but we are not interested in continuous map. And the third technical ingredient is to relax the notion of lattice. Indeed, we need to relax the notion of lattice in order to get a space IPD with simple homotopy type in the following way. Please regard this blackboard as a 2-dimensional space and consider the following region. I want to regard this region as 1-dimensional space in a general sense, in a relaxed sense, because this space has a proper map to the real line. We regard this y direction. We want to regard this y direction as a kind of internal degree of freedom in a general sense, and this x direction is the only spatial direction. By considering this space as a generalized 1-dimensional lattice in this way, we can solve Kita-X proposal, namely, so we can solve that this map is indeed a homotopy equivalence. This relaxation is known to be necessary in the free fermion case. And I want to tell you what is the homotopy groups of the resulting omega spectrum. This is the point. Indeed, we know very few about the homotopy groups of the resulting omega spectrum. Very few. We know that we can fill the table of the right half here. So by Kita-X proposal, this homotopy group it depends only on the difference n minus d. This is a consequence of the Kita-X proposal. This group depends only on d n minus d. And we can draw, we can fill the table in this way. We know that the degree 2 is isomorphic to z. This corresponds to the Berry curvature. And minus 1 to 0, 1 is 0. This is trivial. And the homotopy group with degree more than 3 are all trivial. This is all what we know currently. And there is a fermionic analog of this space, and we know this space is more complicated in this. There are 3 non-trivial homotopy groups known, Z2, Z2, 0Z. And this Z2, Z2, 0Z is very similar to the Vought periodicity appearing in the homotopy group of the real case theory, Z2, Z2, 0Z like this. And indeed, we can compare these two Z2, Z2, 0Zs by a canonical map from free fermion to fermion. So this is all what we know, and our knowledge is very restricted. But although we know very few about the table, in this also we know very few. Kita-X conjecture has an effective application to SPT phases in low dimension, indeed, and it recovers many concrete studies by Ogata, Artemievich, Kaputin-Sopenko, and also many other results. And also there are some new results which follows from this abstract algebra topology and this table. And okay, I have 2 minutes more. So I want to introduce to go beyond Kita-X proposal. We can immediately consider that to place the set of Hamiltonians onto a general metric space beyond the Euclidean space. It's very natural. And the assignment to assign from X to X the homotopy group of the set of invertible quantum spin systems on X gives a functor from the metric space to abelian group. And indeed, this kind of assignment is believed in field theory to give a generalized homology theory, I think. And it is called the generalized homology hypothesis in some context. And we can do the same thing, but in our setting, this assignment is just an coarse homology theory, not the homology theory, but the coarse homology theory, because our lattice system does not distinguish ZD and the final lattice DD or ZD and RD. There is no we can distinguish the Euclidean space and its lattice. So the point is that the invertible phases of spin our invertible phases does not remember the local topology of the original space X, but in coarse geometry there is a nice idea replacing finite to infinitesimal to obtain some K homology in terms of coarse geometries. This is we can mimic the idea to get the definition of localization flow, which this is my naming. We call a localization of Hamiltonian is a sequence of Hamiltonian. Half infinite paths of Hamiltonians whose interaction range decays as S goes to infinity. This is a very rough definition, and precise definition is much more subtle. Please read my paper. But we can consider the set of such a half-infinite path of Hamiltonians and the set of such a Hamiltonians. Then it forms a Mio spectrum and it satisfies the generalized generalized homology hypothesis like this. And indeed, this gives a model of the homology theory coming from the Mio spectrum algebraic topology argument. Please give me 1 minute more. I'm sorry. And moreover, we can consider the same thing for the situation that there is a symmetry of a crystallographic group. We can consider the crystallographic invariant set of Hamiltonians. This has been, so in the case of translation symmetry, there was some previous research this was the general crystallographic symmetry has not been considered in the context of lattice quantum spin systems, I think. But we can show that we can study this homotopy set, and indeed, there is a kind of Baum conjecture for this kind of subject, namely, so this is an element in here is a set of is a half-infinite path of gamma invariant Hamiltonians. So we can consider evaluating S is equal to 1 to get a single gamma invariant Hamiltonian. This gives a map from here to there, from the set of localization flow to the set of gamma invariant Hamiltonians. And indeed, we can show that this map induces the injective map of pi0 group. And moreover, the left-hand side is very computable because it gives a homology theory. So we can show that the right-hand side, which is very natural to be interested in, has a direct summand which is computable. And moreover, this should be called a quantum spin system version of the Baum conjecture, which has been studied in non-commutative geometry. Okay, this is. I want to finish here. Thank you for interaction. Thank you for attention.
Any questions?
I'm a bit confused about the role of X in the appearing as a, you're setting X to be a homology variable, right?
Yes, homological variable, right?
I thought if it were